Today I'll be going over the exam practice session number 3 worksheet. First question is alpha, beta, exp, minim, x. In this question, player A is a minimizer, B is a maximizer, and C is a chance node. All children on a chance node are equally likely. We're going to look at a game tree that has these 3 players, and instead of just pruning a minimax game tree, we're pruning an exp minimax game tree. So it has an expectimax component and a minimax component. We assume that the children of a node are visited in left to right order. For each of the following game trees, we want to give an assignment of the terminal values to the leaf nodes such that the bolded node can be pruned. But it's okay to prune more nodes. And if there is no assignment such that the bolded node can be pruned, we should write not possible. We should not prune on equality, and the terminal values must be finite. So these are the important details of the question that we'll need to use in order to answer the question. So as stated here, the alpha beta pruning algorithm has cannot say anything about chance nodes because it is an exact pruning algorithm. And so instead we're going to have to see at what point can we guarantee the value of a node even though there are chance nodes in the tree. Okay, so let's look at part A. In part A, I'm going to label some important values that we're going to need to keep track of. So say that the total value of the tree for A is going to be V. This is the, since A is a minimizer, V would be the minimum value that A can get with this one ply look ahead. And I'm going to call this value for this B node X and the value here Y. And then I'm going to call this W and this Z. Okay, so we've got X, I'm going to rewrite that a little better. X, V, Y, W, and Z. So we know from Minimax that V is going to be equal to the minimum between X and Y. Because that's what A does. It takes the option that it can minimize. And Y is equal to the maximum between W and Z, as it's defined because B is a maximizer. So here, in order to prune this node, we need that the value of the second B, the right B, to be guaranteed to be greater than the value of the left B. If we know that Y is greater than X, if that's true, then V will just be equal to X, right? But as defined. And so if we know having only explored up to here, if we can already know that Y is going to be greater than X, then we don't need to keep exploring. That's why the alpha beta pruning works. It's when you know that a node is guaranteed to be above a certain threshold or below a certain threshold such that you don't need to explore any further. So we need to find an X and W such that Y is always greater than X, no matter what Z is. Because if we don't care about the value of Z in order to find the value of V, then we don't need to keep expanding nodes. Great. So the since since y is equal to the max between w and z, that means that we just need the max between w and z to be greater than x. So if w is greater than x, then y is greater than x, because y is the max of w and z, no matter what z is. Therefore, we just need to assign the value such that y is greater than x. So if we arbitrarily pick these all to be 2, then x is equal to 2. And if we set these to be equal to 3, then w is equal to 3. Then y is greater than 3. And therefore, value is equal to 2. Because a would never pick to go right if it can get the 2 on the left. Okay. Okay, so now for part B, we have a similar problem, but the chance nodes have been switched with the maximizer nodes. So again, I'm going to label some values, v, x, y, w, z, and this time also alpha and beta. So v is equal to the minimum of x and y, and y is equal to not the maximum, but the average, so w plus z over 2, and z is equal to the max of alpha and beta. So here v is trying to minimize its value, and a is trying to minimize its value, so v is being minimized, while b is maximizing its value. And if we look here, so the in order to allow for pruning, we want the value of y to be guaranteed greater than x. So if y is greater than x, then we can expand fewer nodes, because if y, so we want to guarantee that y is greater than x in order to, we want to guarantee that y is greater than x earlier than seeing this last node. But since this is a chance node, its value is going to be the average of w and z. So both of those values are going to be important, but we can, if we can guarantee that so we want to guarantee that z is if we can guarantee that z and w together are greater than x, then we're fine. In order to guarantee that, we need we can guarantee that by then x is less than y, and so to guarantee that, we can show both w greater than x and z greater than x. So if that's always true, then the average of them will still be greater than x. In order for both to be greater than x, we just need to put values that are greater than x in the b's. So again, we can give x a value of 2, and if we give w a value of 3, and z, since b is a maximizer, if the first node is expansive of 3, then b is at least 3, because b is a maximizer, and therefore z will be greater than x, and therefore y will be greater than x, and therefore v will be equal to x, and we don't need to look at beta. For the last part, we have the same tree as before, but this time we're asked to prune in the middle of the third B. And this is actually impossible, because since this is a chance node, its value is the average of the two nodes below it. So if we wanted to show, so we have this x and y again, and v, and we still want to show that y is always greater than x, because that would mean that we can prune nodes that are under y. But here, y is the average of w and z. So even if I were to put like 100, so if, let's say I have my 2's again. If I were to put 100 here, then an adversary could just say, oh, well, this is actually negative, like, I don't even know how many zeros that is, to bring y down. And therefore we have no guarantees on the value of y, and therefore this is Wait, question 2. This one is about utilities. So here we have this Ghost King and Pac-Man, and they have the same preference order among all possible event outcomes. Does this mean they have the same utility function? Maybe not, because they have a different preference order when it comes to lotteries. So we have U, G, K, and UP to denote the utilities, and they're guaranteed to be non-negative. Here we're asked, for the first question we're asked, which of the following relations are consistent with this observation. So we can look at them one by one. So the first one is that Pac-Man's utility function is just a affine transformation of the Ghost Kings. So for example, if the Ghost King's utility function were this line, then Pac-Man's utility function could be this line. This utility function, this transformation preserves ordering for events, but it also preserves ordering for outcomes, for lotteries, because it's just like shifting the numbers around without actually shaping them any differently. And for a here we had a number. The first option would have a smaller slope, and the second option has a larger slope. But both of these preserve ordering for any case. the third option, we have UP would be the square of UGK. So here we can see that it, so first of all, it preserves ordering for normal events because it's monotonically increasing for non-negative values, which is good for the first part. But for lotteries, we see that they're different. For example, if I have a lottery between 10 and 5, then UGK of this lottery, if UGK, let's say UGK of 10 is 10 and UGK of 5 is 5, that means that UGK of this lottery L is equal to 7.5, assuming both are equally likely. But UP of 10 is 100, and UP of 5 is 25. So UP of L is equal to 100 divided by 125 over 2, which is 62.5. If the Ghost King was offered to get 7.5 immediately without a lottery, the Ghost King would be ambivalent between the lottery and 7.5. On the other hand, Pac-Man, if it were offered 7.5, that would be Pac-Man's utility of 7.5 is 56.25. So Pac-Man would prefer the lottery over getting the expected value of the lottery because of this nonlinear transformation. So this is a correct answer. And the fourth option is just the same thing in reverse. So this is also a correct answer because it is a utility function that preserves the ordering with respect to outcomes, but not lotteries. Now we look at part 2, where we're trying to find which one makes Pac-Man more risk-taking. So being more risk-taking means that you would prefer the lottery over the expected value of the lottery. So as we saw from the previous part, that was the third option, where Pac-Man prefers 62.5 over 56.25, or the utility for the lottery is 62.5, even though the expected value of the lottery would give Pac-Man a utility of 56.25. Now we look at whether Pac-Man would take a deal on a lottery. So we have this ghost vendor that has a lottery of 1, 4, 5 with equal probability. And we're saying that the utility function can be either m or m squared, where m is the number of dollars won in the lottery. So here there's this deal option. So Pac-Man can pay $1 and will always get the highest reward possible. Okay, so for this problem, I'll first look at what the utilities are if you choose to pay. So here we're going to pay, and we're going to see what the utilities are. So for the if the utility is m, then we get a guaranteed probability of 1 times 5 minus 1, which equals 4. So you get a utility 4 if you pay, and you have the first utility. If your utility is m squared, then you get a guarantee 1 times 5 minus 1 squared, so you get 16. Now what happens if you don't pay? If you don't pay the first option, where u of p of m is equal to m, then we have a 1/3 chance of getting 5 plus a 1/3 chance of getting 4 plus 1/3 chance of getting 1, which is equal to 10/3. If we have a utility of m squared, then you have 1/3 times 25 plus 1/3 times 16 plus 1/3 times 1, which is equal to 14. Okay, so now for the first option, so we're asked which of these would Pac-Man be willing to pay. And so for the first option, we have 4 if you pay, and this is 3.333. So you get more utility, Pac-Man will get more utility if Pac-Man pays. And for m squared, we have 16 versus 14. So again, Pac-Man is willing to pay for the highest possible reward. Now, what happens if the deal is changed, and instead you can only guarantee that Pac-Man never gets the lowest reward, and the remaining outcomes become equally likely? So then we still have the same options, pay and don't pay, and m squared. So if you pay, then you have probability of 1/2 times 5 minus 1 plus probability of 1/2 times 4 minus 1. You can't get the 1 anymore, but you still have to pay. So this gives us 4 plus 3 halves, which is equal to, 2 plus 1.5, which is equal to 3.5. And if you have m squared, then you have probability 1/2 times 5 minus 1 squared plus 1/2 times 4 minus 1 squared. So we have 16 over 2 plus 9 over 2, which is 12.5. And if you don't pay, then you just get the same numbers as above, 3.333 and 14. So in this case, 3.5 is greater than 3.333, so M is still willing to pay, but 14 is greater than 12.5, so this one is not willing to pay. If you have a utility function of m squared, the lottery is more exciting than paying for a slightly better lottery. Yep. And that's it for this sheet. Hopefully that was helpful.